Namaskara. We have seen depth first search and a skeletal form of the depth first search. Depth first search in its vanilla form will look like a simple recursive program, but it has got several control points at which we can meaningfully insert additional computational steps. What kind of computational steps to be inserted where is what we have seen in depth first search skeleton. Here is a canonical example where that skeleton is going to be filled with meaningful computations. We are going to solve the problem of finding the cut vertices of a graph. We are working on undirected graph for this case. So let G be a connected graph. A vertex V is a cut vertex if its removal disconnects the graph. For example, in the graph shown in the picture, vertex D is a cut vertex. You remove it, you can see that several pieces are created. A, B, C, E, F, G, these are all different pieces. It is disconnected. So D is a cut vertex of a graph. B or F is not a cut vertex. You remove F, still you have a connected piece remaining there. Okay. So we have seen that problem solving begins with a mathematical thinking, and then we see how to proceed with computational thinking. Finally, we translate that into algorithmic thinking. Our problem is to solve the cut vertex problem. That is, you are given a graph, you have to say which vertex is a cut vertex and which vertex is not a cut vertex. So every cut vertex is going to be labeled. This is a cut vertex, this is not a cut vertex, and so on. So you can have a attribute CV, so that V dot CV equal to 0 if V is not a cut vertex, V dot CV equal to 1 if V is a cut vertex, right. If it is not a cut vertex, this is when V is indeed a cut vertex. Very simple, a Boolean flag. We have to determine this. So mathematicians have a way to say which vertex is a cut vertex, which vertex is not a cut vertex, if and only if, characterizing the condition. A vertex V is a cut vertex if and only if there is a pair of vertices x, y such that every path between x and y contains V. Look at the way in which the cut vertex is characterized. It is a beautiful theorem, and nice proof of this is also available. But is it possible for us to arrive at a computational process based on this characterization? It is an if and only if. So think for a moment, you have a vertex V, you must find out a pair of vertices such that all paths between that pair of vertices must contain V. So you take a pair of vertices, enumerate all paths and check V is in all paths. If V is not in all paths, you have to work for another pair. Maybe this is not the pair, it is another pair. Again for that pair you have to enumerate all the paths, and in each path whether V is there you have to find. And number of paths can be exponential, and there is no convenient way to enumerate all paths. Very complicated task. Therefore, while this is an interesting mathematical characterization, it does not lead to a convenient computational process. So we are going to think in a different way and then arrive at a new characterization. But with this new characterization, it is easy to devise a computational method. Okay. So, let us view G in terms of tree edges and non-tree edges. So, you perform a DFS, and with respect to a DFS you will have tree edges and non-tree edges. All non-tree edges are called back edges because they take you from a descendant to an ancestor. So, it will be like this. There will not be a non-tree edge like this. There will not be a non-tree edge like I have marked in red. The reason is simple. If that edge were there while exploring this node, you would have considered that non-tree edge and then you would have included it. Therefore, there will not be any non-tree edge going to some other part of the tree. All the non-tree edges will go only to an ancestor. That is why they are called the back edges. We imagine the tree is growing downwards, the non-tree edges will take you to an ancestor. So, it will be like this. So, consider a vertex u, and during the exploration it will explore a child, and after finishing it will come back to u, and after finishing with V2 again you will come back to u. The exploration goes recursively. Suppose you have a child that does not have child, or its descendant does not have a back edge taking you beyond u, like in this picture V1. But for V2 you can see there is a back edge from a descendant of V2 going all the way up. It will be going over and above u. Similarly V3. If this is the case, removal of u is going to disconnect V1, because V1 and its descendants are maximum connected with u. If u is removed, then these nodes have no other connection to anywhere else. The graph gets disconnected. That is the reason why you have to see whether a node has a child which may become an orphan if that node is deleted. If u is deleted, V1 will become an orphan. V1 gets completely disconnected, right. So, motivated by this, we have a definition. Low of u is minimum over V dot d, where V is a vertex reachable from u by using 0 or more tree edges and 0 or 1 back edge. Okay. In the most general form, from u you go through some tree edge and one back edge, one single back edge. So, what is the earliest visited vertex you can reach by this process? From the node, walk along certain tree edges and then use one back edge and then find out where you can go through that back edge. So, whenever there is a back edge found, the other end of the back edge and its discovery time is going to be recorded, and it is a minimum of discovery time. So, low u is going to be computed in the following way. So, first observe that minimum of V dot d, where V is reachable from a descendant of u by a back edge, and this quantity is nothing but minimum of low of V, because V dot d minimum is nothing but low. So, also note that all values needed to compute low u are not available in one place, so that you can compute easily the minimum. You have to compute low value by looking into the relevant values as and when they generate. So, during the exploration at different points, the relevant values will be discovered and you use them to update the minimum. So, low u is nothing but minimum of low u and v dot d, where u v is a back edge, it is going from u, because from u with no tree edge and one back edge, that means let u be the vertex and with no tree edge and one back edge means from u you may have several back edges, each going to some vertex, and we are interested in the one that has got the minimum discovery time. Therefore, low u in this case captures 0 tree edge followed by 1 back edge, no tree edge is involved here. Low v for a child can be recursively computed and low u is updated as minimum of low u and low v, because if you go one step down from u, you get a child v. From here, whatever is the low that you obtain is done by one tree edge followed by 0 or more tree edges followed by one back edge. Therefore, low v gives the when you recursively compute, it gives the vertex that can be reached from v or its descendants. Okay. Therefore, in order to compute the low, all we have to do is the following. We add u dot low equal to u dot d at control point 1. Control point 1 is when it is discovered. So, u dot low is u dot d. This step is to be added at control point 1. Now, when you backtrack from a vertex v, you have to update low of u. So, look at the control point 4. So, in control point 4 we have to include the computation to be done while backing from v to u. While backing from v to u, you are updating the low of u by finding the minimum. That is what is done here. Therefore, this must be added at control point 4, and when there is a back edge, we have seen u dot low is minimum of u dot low come v dot d, and this must be inserted at control point 5, because control point 5 is where the computation related to back edge are to be done. So, this is the step that you have to add at control point 5. So, when you fit in these steps into the skeleton, it becomes an algorithm finding the low of a vertex. Low of all vertices can be computed. You just do the DFS. During DFS, at various points you do various computation that would solve the problem of finding the low for every vertex. Okay. But finding the low of every vertex, you can see here is the DF as low of G. For each vertex u dot color is white, u dot p is nil, u dot d is 0, u dot low is 0. Now time is 0, DFS low GU, DFS low GU is found like this, time equal to time plus 1, u dot d equal to time. This is the depth first search. What is that I have added? U dot low equal to u dot d. This is at the time of entry. Therefore, at control point 1 you can see a step is added. What is added at control point 4? This is control point 4, this is control point 1, this is control point 4, this is control point 5. At control point 5, whatever you have to do for the back edge is added. At control point 4, whatever you are supposed to do for backtracking is done. Therefore, this completes the specification of the algorithm. See how elegantly during DFS, in the skeleton of DFS, by adding certain steps, you are getting a solution for a problem. We have not yet solved the cut vertex problem. We have solved a problem of generating a very useful information, and that is called the law of a vertex. The law of a vertex is useful in coming up with a new characterization of a cut vertex. You can see that a vertex is a cut vertex if and only if a vertex is a cut vertex if and only if there is a child v of u in the DFS tree such that law of v is greater than or equal to u of d. Okay. If this is the case, law of v is greater than or equal to u of d. If this is the case, u is a cut vertex. Why u is a cut vertex? U is like this, v is like this, law of v is from v you can go down and then go to this and back edges, from v also back edges, wherever maximum it goes is only up to this. It is not going above u, because law of v is greater than or equal to u dot d. All back edges, tree edges are clustered here. So when you remove u, v will be orphaned. In other words, u is a cut vertex. So u is a cut vertex if and only if there is a child v of u such that law of v is greater than or equal to u dot d. But this characterization is true for root, right, because discovery time of the root is 1. Any other vertex will, therefore this characterization should not be applied for the root. The root will be a cut vertex if it has got degree more than 1, because this is the root of the DFS tree. If the root has got degree more than 1, naturally its removal will disconnect the graph. Therefore, root is a cut vertex if and only if it has more than one child. Therefore, your algorithm becomes much simpler. How do you find a cut vertex? U dot CV equal to 1 if u is a cut vertex, otherwise it is 0. All we have to do is that if u is not the root and v dot low is greater than or equal to ud, u dot CV equal to 1. Only this has to be added at control point 4. That is it. When this is done, you have solved the problem of finding the cut vertices. The whole solution emerges as a magic. Okay. Initially things were complicated, but with a new characterization, we were able to finish the task of finding the cut vertices in a very easy manner. Okay. This is the power of algorithmic thinking. You start with mathematical characterization, but if that mathematical characterization is not satisfactory, find new characterization. Depth first search allows you to find some values which are helpful in arriving at a new characterization. Use that characterization to determine whether a vertex is cut vertex or not, and this can be done on the go. Therefore, we have a linear time algorithm for finding all cut vertices of the graph. Extremely elegant and simple one. This shows the power of DFS, how at various control points of DFS, by adding additional meaningful computational steps, we can design an algorithm solving a graph problem. Okay. I conclude at this point. Thank you.